Okay, so looking at reactions, there's a few specific things we want to touch on before we move on. Some things that we didn't get to the specifics on Friday. Last Thursday. This out of the way. So when we look at the reactions, let's look at kinetics. And we talked about how kinetics was how fast something worked. What we specifically need to know is rate law. And the rate law is going to be the rate equal to some constants times the concentration of the reactants. Okay, the reaction factor here is constant for each specific reaction. And so it's usually something that's determined by the reaction. And then you can speed and slow up a reaction by changing the concentration of the reactants based on that K. So you would do an experiment to determine K, and then you can calculate that. For most of the stuff we're going to be doing organic, we're not going to actually do the mathematics of this. What we're going to be looking at is if we looked at A plus B going to C plus D, what we want to know is this rate law something that is second order, right? Or is it something that is first order? If we look at second order, what the second order is saying is that both A and B are involved in the rate determining step. Right, the RDS. So if I do an experiment and I find out that a reaction, both the concentration of A and the concentration of B will impact the rate of that reaction, then I know that in the slowest possible step of the mechanism, that both A and B are involved. Okay. If we look at first order, then we know that only A or B, depending on which one it is, but in this example, only A is in the rate determining step. And what this does is allow us, let's say that we looked at our example the other day, we have alcohol is going to displace a chlorine, become this alcohol plus chlorine. If we look at this reaction, the rate of this reaction, if we found experimentally that it was based on the concentration of this and that, right, and based on what we looked at last Thursday, right, we said that this was all a concerted mechanism where this all happens in one flow. Make sure that has a double barb, right? So since concerted, it only has one step. If it only has one step, that's the rate determining step. And so the rate determining step here, right, would have both of those. If we looked at our other example, right, if we look at something like this, if we found the rate in this reaction, only the concentration, and again, this would be experimental, but if we found that that was only the concentration of that alkyl halide, then what that's saying is that this is the rate determining step doesn't have water involved, right? So our water is not involved in rate determining step. So The rate determining step is that. The whole speed of this reaction is going to be determined on how fast that the alkyl halide can dissociate to the carbocation and the chloride anion. So rates can help us determine processes. So as we look at rates, so if something was a second order rate, that means that there's two things involved in that step. If it's a single order rate, it can tell me that there's only one thing, which means there has to be more than one step, right? So by default, if it is a first order and there are two things reacting, it has to be more than one step. And it can tell me which steps are going to be the slowest steps. Okay, so we'll come back to this several times throughout the semester. Let's talk about Gibbs free energy a little bit more. So again, delta G equals delta H minus T delta S. And we talked a little bit about enthalpy, right? So delta H is enthalpy, delta S is entropy. Although there's several things that go into enthalpy, you can think about it primarily. Now there's several things that go into it, so it's not only this, but you can really think about this as bonding and bonding strength, right? What does it take to break? And what do I get for making? Right, so the breaking and the making of the bonds. How strong are those bonds from the reactants to the products? Okay. For entropy, that's really has to do with order. And the things we'll be looking at will be degrees of freedom, right? Degree of freedom is if I have an acyclic, it has more points to rotate, right? So that'll have a higher entropy than if I have a ring, right? But a ring will be more stable, meaning it shifts to enthalpy. And then we did show this, but the book was very specific, so I want to be specific. When we look at this energy here, the difference between where we start and this highest is the delta G double dagger. And when you see that double dagger in the organic coordinates, that means transition state. Okay, so that's the delta G that you have to get over to get the reaction to go. This difference here is the delta G for the reaction. So it's the change in the delta G for reaction. This will tell me if it is exergonic, right, or endergonic. And exergonic is, if you think about different processes, right, exergonic is going to be out, so energy going out. Endergonic will be energy having to come in. And what we're doing here is really kind of going back there and getting some of the specifics that I missed last Thursday. So equilibrium, again, you should have covered this pretty in depth last year in general chemistry. What a quick overview. Now notice here that the Y, I mean the W, X, Y, and Z, those have to, those are the coefficients, right? So when we look at a reaction, those are the coefficients. So when we're looking at the equilibrium of the reaction, the equilibrium constant is going to be products, the concentration of products over the concentration of reactants. And last week we talked about the fact that you could, you know, force a reaction to go either backwards or forward based on concentrations. And that's what we're talking about is the equilibrium. There are some reactions that really have a high K value, right? They're really shifted one side or the other. But really we're moving away from the idea that everything is a static reaction. The reaction occurs and that's it, right? There's always the possibility of equilibrium. In some cases, the energy it would take to get a reaction to go backwards would be more than the energy than the molecule could withstand, meaning if you tried to reverse it, you could destroy the whole molecule. But the concept, it's almost like when you go from algebra to calculus, you have to think about limits, right? Here, when we start thinking about organic reactions and we start thinking about more advanced reactions, you have to start thinking about not precipitation reactions. Why are precipitation reactions not an equilibrium reaction? Not because they couldn't go backwards, but because it precipitated out of the solution. It's no longer in the solution to react. So therefore, almost everything is an equilibrium reaction, meaning everything can potentially go forward or back. The question is, does it go forward and back enough for us to worry about it? All right, so it's a slight change in the way we perceive chemistry. It's not A plus D always goes to C and never goes backwards. It's that A plus C will favor C, and A plus B will favor C, but there should be a possibility that I can reverse that. Okay. So when we look at this, what that means as far as our formula, products over reactants, we'll have C to the Y, D to the Z, right? So as we look at this, we involve the reaction coefficients as, you know, could be, if it's 1, that's no problem. If it's a 2, it's square. If it's 3, it's cubed, so forth, so on. So if our products, when we put reactions in the solution, right, and let them go, if the products outweigh the reactions, then we're going to have a positive K, and that's going to give us a reaction that's going to proceed forward. If we put the reactants in there and we never end up with more products than we have reactants, that means that equilibrium favors reactants, right? So that means that it's going to go backwards. That means that equilibrium, we can use equilibrium experimentally to get us to delta G. So equilibrium constant, the KEQ, is related to delta G by this formula. So remember, if the products are greater than the reactants, that means it's going forward. But for a delta G to be exergonic, forward directing, it needs to be negative. So the first thing we need is a negative. R is a gas law constant, T is temperature, then we need a natural log of the KEQ. So we can actually determine delta G from our equilibriums, right? So that's the way those are related. So if you think about how do we get all of these different things, delta G comes from our equilibrium constant, and that can be experimentally determined. Now, most of these, right, we're going to be thinking about them theoretically, not doing calculations. So you're not going to see a lot of calculations, but you need to understand this. When we look at products and reactants, we need to think about those products and reactants and the concentrations of those to think about an equilibrium constant. You may not have to mathematically determine a KEQ, but conceptually you need to know these things, right? You need to understand that KEQ is related to delta G conceptually, even if we do not calculate these numbers in class. Okay, so when you're looking at these, your concept of this is more important than your ability to plug and chug and get the number out. Okay. Let's touch a little bit more on catalysts. And specifically here, just want to draw the diagram. So if we look at our original reaction, we have our delta G transition state. What happens when I add a catalyst to that is I don't change the starting point of the product, of the reactants, and I don't change the ending point of the products. What I'm changing is the delta G of that transition state. So now the catalyst has got a smaller transition state, so this is going to happen faster. Many of the catalysts that we think about, reactions that don't occur without catalyst, one that you'll see would be hydrogenation of an alkene. Without that catalyst, theoretically this could happen, but the energy of activation, that delta G transition state, is so high that this really doesn't happen. You can do it under a whole lot of pressure and temperature, but that's not a highly effective way to do reactions, right? To bring hydrogen and flammable organic compounds in really high pressures and really high temperatures. What does that bring to mind when you take highly flammable materials and put them under really high pressure and really high temperatures? Yeah, it's a bomb, right? So effectively, that's not a good organic reaction. If you have to blow something up to get something made, that's not a good idea, right? So here in this case, that catalyst drops this energy of activation so much that this is something I can do at room temperature under normal atmosphere and normal temperatures, right? If I pump hydrogen with a little bit of palladium into a solution of propene, I can turn it into propane. Now, why you would want to do that, you probably wouldn't, but anytime you want to take a double bond, really, you might have to heat it up to 35 degrees Celsius, right? Which is kind of Oklahoma on a really, really hot day. Nothing abnormal, okay? Okay. Questions about overall general organic mechanisms and kind of the base level stuff. Now we're going to move into specifics. So let's look at acid-base reactions, and we'll spend a few days on this. So classic acid-base reaction, right? Hydrochloric acid with sodium hydroxide. We end up with sodium chloride plus water. One of the base issues that usually students have when they get to general chemistry, either in high school but more so in college, is that there's actually three definitions of acid bases. And the way to think about them is you have one definition inside of another definition, right? So if it's an acid base here, it's of course going to be an acid base in the outside. So if we look at this first kind of definition, and you might have heard it, acids and bases, right, make water, right? So you might have heard that in elementary school. That's true. An acid and base will make water, but that's the Arrhenius. That's like the old definition, right? That's this little microcosm of acid-base reactions. The next level out is Bronsted-Lowry. And in Bronsted-Lowry, we expand that a little bit and we say, we're transferring protons, right? We have a proton transfer. So under Bronsted-Lowry, if we have a proton moving, right, then we have an acid-base reaction, right? So that expands it a little bit. Here, I'm not forming water, right? I'm forming ammonium, but I've had a proton change. So this is an acid-base reaction. Up here, could a Arrhenius acid base be a Bronsted-Lowry acid base? Yes. Do I have a proton transferring? Yeah, I have a proton transferring, right? I have movement of a proton. When we go to the outside here, right? We're going to expand this definition again, and we're going to look at Lewis acids and bases. And in this case, and I'm going to switch my colors. In this case, I have a lone pair here. All right. So I have electron, I have available electrons. And then over here, what do we know about the aluminum? Aluminum is in the third column, right? And it only has 3 electrons. And if it's only attached to 3 things, then what is the hybridization of aluminum? Well, aluminum is going to be sp2. And if I've hybridized sp2 to react with those 3 chlorines, what's left over? What's left over is an empty p orbital. Right? So I have an empty p orbital in aluminum chloride. I have an empty p orbital in boron, right? They are stable without an octet. They are stable with 6 electrons. So therefore, they have an empty orbital. Can an empty orbital accept electrons? By definition, yes. There's nothing there. It can accept electrons. Whether it is more stable or not, we'll have to investigate that. But can it accept it? Yes. So if I have a carbocation with empty electrons, the carbocation can accept electrons. So what Lewis acid base does is it expands out the definition. So now it is a transfer of electrons, right? From electron rich to electron poor. And we end up with this zwitterion. And zwitterion is just a species where we have positive and negative next to each other, but they don't bond, right? So a zwitterion is a positive and negative in close proximity, but bonding availability, molecular orbitals are not there to allow them to fully bond. So they just stay as ions. So they have formal charges next to each other, which it seems weird, right? But the reason they stay that way is because the orbital structure, this is more stable. Okay, so we have Arrhenius, right? That goes all the way back to first grade. And then we go Bronsted-Lowry. You've been dealing with that one for a long time. What we're going to be doing more with in organic is this Lewis acid reactions. So we have multiple. So if there's a proton transfer, that's easy. If there's a proton transfer, that's acid-based. You'll notice those all the time. But anytime we have this kind of electron rich going to electron poor, right, that also is an acid-based reaction under the Lewis acid base, which means that a lot of the reactions we're looking at actually come back to that Lewis acid base reaction. So some of the reactions we're going to do later on, we're going to define them as a substitution, but at their base, they could be seen as a Lewis acid base type reaction. Now you'll be asked, where is the question on here? Well, then the question is, and again, because Arrhenius is past, what you'll be looking at are questions around identifying Bronsted-Lowry acids and bases and Lewis acids and bases. So one of the questions that comes out of this definition is just, can you identify? So let's try that. I'll put some reactions down, compounds down. Tell me if this is Arrhenius acid, Bronsted-Lowry acid base, or if this is a Lewis acid base. So think about those definitions and let's take about a minute. Okay, so let's take a look at the first one. We have a phenol here. This is a phenol. And we have a hydrogen attached to a hydrogen bonding hydrogen. Could we take that and form this? Yes, right? So that means that this could be a Bronsted-Lowry acid, right? It could be a proton donor. Will it be a proton donor will be determined on whether that is equilibrium forward, positive, right, or if it's equilibrium negative, right? Is it pretty stable as the phenolic compound, or is it more stable as the phenol? Could this also be a Lewis base? Yes. Right? So that could also potentially be a Lewis base because it has a lone pair. So it could behave as a Lewis base by giving its electrons to something. Yes. Both. Because it's an electron donor, right? This one, of course, is because of the negative charge, and it's obvious. But could this lone pair here, right, in a more acidic solution, could it pick up a proton? Yes, it could pick up a proton because it has a lone pair, right? So this compound could both act as a Bronsted-Lowry acid, but because of that lone pair, it could also behave as a Lewis base. Now, how it reacts will depend on what it's react with. If it is in a basic solution, it's going to behave as a Bronsted-Lowry acid. If it's in an acidic solution, it potentially would react as a Lewis base. Okay. Let's take time to think about that because this is part of the point where it's going to get pretty complex pretty quick. How something behaves is often what it's reacting with. The simple definitions are simple, right? Is this a Lewis base? Yes. Does it have lone pairs that it can give away? Yes, it's a Lewis base. Will it be a Lewis base? Depends on what else is in the solution. Could it be a Bronsted-Lowry acid? Yes, it has a proton that could be transferred, right? So therefore, it's going to be a Bronsted-Lowry acid. Okay. Yes, ma'am. Sorry. Yeah. Yes, but the definition potentially can be different, right? So the Bronsted-Lowry acid and base definition is different than the Lewis acid base. So if it is a Bronsted-Lowry acid base, it's also going to be a Lewis acid base. So this could potentially act, right? So that's a very good point, right? So let's put this down on paper. So Bronsted acid is a proton donor. So if we think about the Bronsted-Lowry acid point up here, and I guess the question is this only a Lewis acid base, or is it also Bronsted-Lowry acid? And it's a Bronsted-Lowry because it has a proton, right? Now, because it has that proton could accept electrons, so therefore, by default, it's also going to be Lewis acid. So this is almost like what we're looking at with this is like what we're looking at for intermolecular forces, right? Every molecule has van der Waals, right? Some molecules have dipole moment. Some molecules have hydrogen bonding. Some molecules, but everything has that, right? Most things can be a Lewis acid and base. Not everything, but most things can be a Lewis acid base, right? But then if it is a Bronsted-Lowry acid base, we have to look specifically at proton. Can it donate a proton, or can it accept a proton? Okay. So the next one is a little simpler, right? Here we have hydrogens attached to carbons. Are any of those hydrogens carbons what we would think of as being available? Can I pull a proton off of a carbon and have a stable molecule? No, and we'll talk about that more, but if we think about these are not hydrogen bonding hydrogens, this is carbon negative is not a very stable species, right? So really what we have here is we have no available proton. How about electrons? Do we have an electron acceptor or electron donor? Well, we don't have electron density, we have electron hole. And because that is sp2 carbon with an empty orbital, right, the positive empty orbital, this then becomes a Lewis acid. So if this was going to react as an acid-base reaction, this really only has one choice, right? So this would be a case where it's outside of the Bronsted-Lowry. It doesn't fit in that. It only is in the Lewis. It doesn't have electron density to donate. It has electrons that it can accept. It can accept electrons because of an empty orbital. This is going to be a Lewis acid. The bottom one is very similar to the top, right? It's both a Bronsted-Lowry acid and base, and it is a Lewis acid and base. And it depends on how it potentially is reacting and what it's reacting with, depending on what it's going to behave as. The second one, if we look at that one, this last one here, do we have any hydrogens that could be available? Again, all of our hydrogens are attached to carbons. They're not attached to highly electronegative atoms, right? So they're not going to be available. So we're not in the Bronsted-Lowry range. We're not talking about protons being donated or protons being accepted. But what do we have? We have available electrons that can be given away. Where are those available electrons? Well, it's in this pi bond. Now, would that break that pi bond? Yes, if I gave away those electrons, it'd break that pi bond. Okay. But this would be a Lewis base, or I could put it in the classification of a Lewis base because it has electrons that it could donate. Now, most Lewis bases you're going to see at this point are going to be lone pairs or negative charges. But you can also, because of the orientation of those p orbitals in pi bonds, they will also have electron density that is available. So they are more electron rich than a normal single bond, right? They're not used to connect the bond, they're outside of that bond. And because of that, they are available. Yes. Lewis base, yes. Okay, now let's look at Ka. And for this, let's look at HA, generic HA plus water going to A minus plus H3O plus. So if we look at a classic acid-base reaction, this is what's going to occur. We look at KEQ, that's going to be the concentration of our products, the A minus and the H3O plus over HA. And since most of the reactions we're going to assume are in water, right? And if they're not in water, we assume that they would be in water. Okay. We need to make an assumption, because if we look at the KEQ for normal acid-base reactions, especially those reactions that are water soluble, those reactants that are water soluble, what's the concentration of water always going to be? Well, it's always going to be really, really high, right? Because it's a solvent. So if we look at the KEQ here, if the solvent is part of our KEQ, that makes it difficult for us to see minor changes in reactions, right? So therefore, what we'll do is we'll drop out the water. We'll say Ka, right? Assuming that we have a solvent as water. So if we looked at the reaction we did above, our Ka for this it's going to be this concentration. Even though we're not using water in this case, we're going to drop out that, and that means that this Ka here is going to be specific for, and this here we could actually determine it as this compound, right? You could put in a generic. This Ka is going to be related to, you know what? This is one step too forward. So sorry, redraw all this. Let's not skip a step. So let's put water in there. So this Ka is going to be related to the carboxylic acid. We don't use Ka very often. We use pKa, and pKa is negative log of Ka. And there's going to be a set of pKa's that you need to know. The first one that you need to know exactly is the pKa for water, and that's 15.7. And then if we look at functional groups, we can think about something like, let's say, H2SO4, right? That's -7, right? So the pK is really high. If we look at H3O plus, right? Now we're talking about 0 pKa, and again, we're talking about negative log here. We look at carboxylic acids. Right, our pKa range is 4.5 to 6. We get to ammoniums. And it's obvious, as we go down this chart, it's going to be a little bit more difficult to see, but it's pretty obvious when we get to some of these what the proton is that we're talking about. So an ammonium, there we're talking about 5 to 7. Alcohols, we're looking at the 15 to 16 range, up to even 18. Again, near water, that would make sense. pKa's are good to know because they can give you a quick reference of how acidic a proton is. And we'll break down some of these and we'll talk a little bit about which ones are. So pKa values, you should know the functional group pKa values. I'll check the textbook and make sure it has a good chart. If not, I'll provide one for you of good pKa values for functional groups. Okay. But we can see here as we go down, right, we start with things that we really think of as acids, right? So our normal strong acids are hydrochloric or sulfuric acid. The pKa values are actually negative. When we get to things that are, well, the quintessential acid, right, H3O plus, we're talking about 0. Then we get to carboxylic acids, right? We're dealing with, around 4.8 would be acetic acid. So we're in this range here, depending on what the structure of the R group is. Ammonium, right? Oh, and I didn't draw a positive. Please correct that. There should be a positive there. So for ammoniums, right, we're dealing with a little bit less acidic than that. Get to alcohols, right? They're like water. Again, 15.7 is the number you need to know. It gives you a reference point. And we notice that our alcohols are here, and we'll talk about the difference between carboxylic acids and alcohol reactivity in a second. And then we get to aldehydes, ketones. They're about in the same range. Esters and other carboxylic acid derivatives that aren't carboxylic acid, right, are in the 25-ish range, 25, 28. Amines, now this amine, right, would be in H2, right? Notice there's not the plus there. There's only 2. We're losing a proton off of that nitrogen. And then alkanes, we can think about alkenes are about in the same place. We're about 50-50, right? So if we think about the acidity of a normal organic alkane, it's really not acidic. And it's about 50. If you look it up in books, you'll see everything from 47 to 72. 60 is often used. The reason is it's getting so low in its acidity. And remember, this is pKa, so this is log. right? So this is a negative log. So when we get up to those sizes, we're talking about minuscule um, Kas, right? We're talking about minuscule protons are going to leave this compound, right? So the smaller they are, the more acidic they are, the more they're going to shift towards the products, right? Right, and log, right, that means that every time we change a number, that's 1,000. So the difference here is not 1, the difference here is 10,000, right? If we look at the equilibrium, we're changing from about 4, I mean, if we change from 4 or 5 to 7, that range is a 10,000 range. Okay, so let's talk about, so this is pKa. I'll get you some values on this, but let's talk about where the pKa's come from and looking at the stability. So if we look, if I'm going to compare this, which I know has a pKa value of about 4.8, and if I'm looking at this, and let's go ahead and make it isopropanol, which has a pKa, I think this one's like 14.9. Don't hold me to that. So these are our pKa values. If we're looking at these two compounds, is it obvious why one is so much more acidic? And again, remember it's 10, but that's 10 magnitude, right? So we're talking about, a 1%er salary versus mine. We're talking about, trillions and trillions of difference here. So when we're looking at this, is it obvious when we look at these that there's a difference? They both have an oxygen attached to a hydrogen. It should be, as we continue through this, you'll start to recognize that hydrogen attached to an electronegative atom like oxygen, that hydrogen is the one we're looking at, right? So it's going to be this hydrogen, right, that we're looking at. Oh, sorry, I uncircled all of them. But it's this hydrogen that's going to be the stable one. They're both kind of the same size, right? Looking at these structures right here, it's difficult. So what we want to look at is the stability of the conjugate base. And a conjugate base, the conjugate is thinking about after I remove that product. You can have conjugate bases, you can have conjugate acids, right? So a conjugate acid is after I've added the proton or after I've given away the electron. Conjugate base is after I've removed the protons or after I've accepted the electrons. So what we're going to look at is not compare this, but we're going to compare its conjugate base. Because remember, what's going to happen in these reactions is we want to know the equilibrium rate for this to go to, and for right now, right, we'll just put the plus out here, right? Now, can you think about the stability of these two conjugate bases? And why? If we look at the first one, does it look stable? Does it look like a molecule you've always seen? Yeah, yes, right? When we go to the second one, what's present? I got a negative charge. What have you already learned about negative charges? Negative charges want to be what? Stable. They're going to react with something, right? They're going to react with something to make more stable molecules. So by showing that negative, by showing that positive, I've already changed in your mind the way you perceive this molecule. This negative is not stable. Because that's the way we've been looking at things, right? Things that are neutral, right, are more stable than things that are positive. Now, that's not always the case, right? And as we go through the semester, you're going to learn that. But what we have here, right, is now we have something to compare that makes us think, I need that to be stable. So what we can think about is what possible things could make this stable. So let's look at this and that as far as stability. Okay, one of the first things we can look at is just the atom. All right, so just as an example, an oxygen negative is going to be more stable than a nitrogen negative, more stable than carbon negative. Why? Electronegativity of the atoms, right? How well it does with that excess electrons. So first thing we can do is just kind of compare our atoms. In this case, both atoms are the same, right? So we're pretty good there. The other way we can look at atoms, right, is going to be looking at size, right? So bigger atoms usually can differentiate that size. So if we look at a iodide ion versus bromide ion versus a chloride ion, the iodide ion is more stable than the bromide, more stable than the chlorine because of the size of the atom, right? So we have electronegativity and we have size. How well can it delocalize that negative charge throughout the atom? So that's the first thing we need to compare. If this had been between oxygen and carbon negative, I could stop right there. The oxygen negative is going to be more stable than the carbon negative, right? By a wide degree. But here we both have oxygen negative. So the next thing we want to look at is a resonance stabilization. So if we look at the first one, can I draw a resonance contributor for this one? Yes, right? So I can say that these lone pair go up here, that goes up there. Right, and I get that species. So I've got this resonance contributor going back and forth. Do I have a resonance contributor for the other one? No. Okay. So that means that this negative charge is isolated, and it's all on that oxygen negative, but over here, it's delocalized, which means that in this case, I'm dealing with partial negative and partial negative. And for this pair, the example gave, this is the difference, right? One has resonance contributors, the other one does not. So the resonance contributors makes one much more stable, right? Makes the conjugate base much more stable, which means the acid. So think about the conjugate base more stable, acid stronger, right? Because the acid will go to the conjugate base more because the conjugate base is more stable. Now, in this case, we found the difference, but let's look at the one of the last things you need to look at. So you start with the atom, right? That's going to be a big difference. Then we look at conjugate. Often, sometimes you have to look at both of those together. But if you find conjugation, right, you can usually stop there and you don't have to go to inductive. What is inductive? Inductive is going to be looking at the comparison between these two, okay? If we look here, right, we have the isolation of the electron, and really there's no electronegative atoms anywhere to do anything. But here I have a dipole moment to pull that density towards the chlorine, right? The chlorine is electronegative. I can pull the electron density toward itself, which does what? If this species is becoming partially positive, what does it want? Well, it wants electron density, right? So therefore, not because its carbon is electronegative, but because of this being pulling that dipole, this is now going to pull what? Electron density there. So inductive is not, resonance is fully moving electrons, right? Inductive is pulling electron densities. So here we shouldn't see a tenfold difference, but we might see several decimal points. Enough for us to say that this compound is more acidic than this compound. And that's another way of saying lower pKa. Right? Where this one might be, the ethanol might be 15.6. The one with the chlorine might be 15. So when we're looking at these, right, the first thing we have to think about is that looking at a stable molecule is hard for our minds to wrap around the fact that it could be unstable. So therefore, we switch it to its conjugate acid or conjugate base, in this case, the conjugate base, to evaluate it. Once we have it in its conjugate base form, right, now we can compare these two and see which one of these two is more stable. If it's more stable, that means the reaction is going to proceed forward more than it's going to proceed back. If it proceeds forward, it's going to be more acidic. So we can look at which atoms are actually electronegative. So that can do with the electronegativity within a column, or it can look at size going a row versus size going down a column. We can look at resonance. If there's resonance, and resonance is a very stabilizing force because it's spreading out that charge, right? It's taking that charge and it's putting that charge on multiple atoms. And then the last one, we can look at inductive. And in inductive, we need something that can pull that electron density to itself. And once it's pulled it to itself, right, that then can have a effect, a minor effect, but an effect on the stability of that anion or that cation. Yes, ma'am. Yeah, the same thing will happen for a base. So if we look at trying to think of a good example here. So okay, so if we look at these two, right, it's not obvious that there's going to be a big difference, and there's not a big difference, but there's going to be a difference here, not as big as our carboxylic acid. But what we want to do here is look at our conjugate base, conjugate acid, right? So we would go ahead and put a proton on both of these. And then we could compare these two. And if we look, they're both nitrogen, right? So the atom is the same. How about resonance? Do either of these have resonance? Okay. The top one can have resonance. No, the top one doesn't have resonance either. No, so no, neither of these have resonance. Do we have any big inductive effects? No huge inductive effects, right? So therefore, for this case, right, which one is going to be more acidic? It's going to be more difficult to determine, right? Turns out that the phenolic is slightly more acidic because of the pi bonds. The pi bonds cannot resonance stabilize that positive charge, but inductively, and it's not obvious, inductively can stabilize that. Let me think of a better example. And again, I hadn't thought of the opposite. So if we look at this example, now when we compare these two, right, I do have an inductive effect that can cause a smaller inductive effect here, stabilizing or destabilizing that positive charge. I'm sorry. No, the phenyl group has resonance, right? This has resonance, but I can't draw the electrons out here because I'd have to lose a bond. It doesn't have a direct effect to this. It does have a slight, and it would be when we get to this, and we'll get to this in reactions of alkenes. This does have a can't remember the name of it. It does have an impact by the pi density being able to stabilize that positive charge, but it's slight. It's like the inductive. It's very slight. So it's hyperconjugation. So it's a hyperconjugation effect. Okay, but this has the resonance, right? But I can't draw resonance out to the nitrogen to delocalize the nitrogen positive into the ring. Okay. Here I'm destabilizing the positive, right? Which means that this becomes more basic because I'm not stabilizing now, I'm destabilizing. This becomes more basic than that. Okay. So again, I can use the conjugate acid to determine something about the difference in stability over here. Right, and it looks like that's time. We'll continue through this. I'll make sure you get a PKA. I'm going to post some questions on online homework. I'll go ahead and see if I can find some of my old problems to give you. Most of those have answers, so I'll post those. Again, at 10 o'clock, we'll have office hours. We'll go through the exam, and if you have any other questions, if you did not get your exam because you weren't here today, I'll have Sharon scan those, and then we'll email those out to you in the next couple